it's mr squared, or it'll be given to you. I mean, it's basically the moment of inertia is equal to the sum of all these little m's and these ri's squared added up together. So this looks like an infinitesimal summation, which we call, there she is. Okay, so she's got to teach next class for 8 minutes. We'll put her up here for 8 minutes next class. All right, anyway. We'll be at, she can teach all about Bernoulli. That'd be great. All right, anyway, so we got does that probably interferes. All right, then we got I times omega, and angular momentum will be conserved as long as there's no other outside torques or forces pulling on it. All right, so let's just take a look at what some of your, and here's when it's conserved, then the I originally times the omega originally equals the I final times omega final. Because what can happen, the classic thing we always use is the figure skaters. Okay? Classic thing that we always use are the figure skaters. And what that does is, let's say we've got a guy who, when he's got his arms out straight, his I naught is equal to 2.4 kilograms meters squared, and he'll be spinning at, say, 1.6 radians per second. I don't know, you might see this problem when you're doing your homework from chapter 8. All right, and then when he pulls his arms in together, his I final is 1.2 kilograms meters per second. I wonder what omega final would be. That's probably the easiest problem you've had all year. Rashawn's like, yeah, well, why aren't they all like this? Because I can multiply these two and then divide by this guy. Basically, it'd be 3.6 radians per second. So when he brings his arms in, he starts spinning faster, basically, is what happens. Okay? So there's one of your problems. And that's pretty much all we'll talk about angular momentum. It's a cool concept. The main thing is that the I can change. So I think you all did this in lab. Didn't you have a big disk turning? Then you set another disk on top of it and it slowed down, right? Here's what's going on. You're changing your I, okay? And you're getting a little bit more mass there too. So if you got another question, let's say, let's just take a look. I figure since I started kind of late, I'll give you a few helpful hints. All right. Where's your other one? I gave you a, let's say a rotating disk of 0.25 meters has an angular momentum of 0.45 kilograms meters squared per second. That's what its L is. What's the angular speed? I think you figured that out. If you know if it's a disk, if you're given L and kind of given I, can you find omega? Yeah, that's pretty easy. So when it says angular momentum is this, that means it's giving you what L is. All right, and then I think the rest of them are, yeah, then I gave you the one about an ice skater had a moment of inertia. Yeah, I gave you that one. All right. Okay, so let's talk about solids and fluids, okay? Let's talk about solids and fluids. Now, we're kind of shifting focus here. We're slowly shifting focus. Oh, by the way, we're going to take a test a week from today, all right? And it'll cover the last half of 7, all of 8, and 9, because we'll finish chapter 9 Thursday. Easy, okay? And I've got I'll have an assignment for you by tomorrow morning. Okay. All right, so we can do that. Now, so here we go. This is start chapter 9. Let's talk about, it's that time of the semester where we can talk about this. Okay. All right. Now, so you got stress. Right here, Killer Kilway has a test waiting for us on Friday again? Yeah, okay. Stress is equal to this. F over A, okay? Which is the force over the area that I apply the force. That's called the stress on something. All right? So we're going to talk about stress and strain. The strain of something is equal to the absolute value, the magnitude of its change in length divided by its original length. Okay? So stress basically equals strain. Is directly proportional. Stress is directly proportional to strain, and it's equal to it. Stress is equal to it if I put in this, what do they call it? How do they word that? Elastic modulus. Ooh, what a word. Elastic modulus, which will be given to you. This is one of those things times the strain. Okay? So, what we talk about when we're stretching things, and on your test, since we've gotten this far, I will probably give you a problem that'll be like your homework problems that will be waiting for you sometime tomorrow, and they'll be due a week from. Yes, Roshana. I'm sorry.
No, is elastic modulus the same as Young's modulus?
Ah, she's ahead of me. Yes, it's exactly that. Okay, now it'll be Young's modulus for just good old one-dimensional stretching. Okay, there's other like bulk modulus and things like that for three-dimensional and stuff like that. But all we're going to do is Young's. Okay, very good. So here's what Rashawn is saying. She's going, hey, where'd you see this before?
I have a kinesiology class I'm talking about it.
Oh yeah. So in kinesiology, we're going to talk about bones and how they stretch and how they get compressed, and that's exactly what. Okay, so. There's a lot of medical applications here with all this stuff when we look at bones, osteoporosis, and all that kind of stuff because bones lose their mass, things like that. So here's what we're talking about. We've got F over A equals the Young's modulus, which you can look up, which will be, or it'll be given to you on a test, okay, times the change in L over L naught. Okay? Change in L over L naught. So how hard can this be? Well, since Rashonda brought it up, let's go ahead and look at the type of problem that you'll see on the test. Now, you've got two kinds of stretching here. You've got tensile and you've got compression. All right, tensile is where we have tension, where we're stretching things, like if something's in traction or something like that, you might want to stress it in a certain way. Now then, usually, now your book does these problems a little bit differently. So let's take a look at how a question on the test might be worded. It might say something like this: the femur, the upper leg, is the longest and strongest bone in the body. Taking a typical femur to be approximately circular in cross-sectional area with a radius of 2 centimeters. So R equals 0.02 meters, and then the area then would be pi times 0.02 squared. Okay, that's not too bad. We want to know how much force would be required to extend a patient's femur by 0.01%. All right, so we want to extend it. In other words, we want delta L over L naught to equal 0.01%, which equals 0.0001. That's kind of a strange way of looking at it. But if you look at it, delta L is in meters, L naught is in meters, so it's a dimensionless thing. And so, like if I stretch something a half, in other words, or compress it, if, say the original length was 1, and I stretched it to or 2, and I stretched it 1 extra foot, then the change would be 1/2, and that'd be 50%. So it's the same thing. Okay, Same thing. So it's 0.001, and they want to know the force. Well, shoot, I got everything I need. That's not too bad. So F equals y times delta L, or L naught, times A. Okay? And that comes out to be pretty strong. Pretty strong. It comes out to be about 1.9 times 10 to the third newtons. Oh, because y is given too. Here, I'm sorry. Y for a bone, when we stretch it, when we stretch a bone, it's much stronger. It's much harder to stretch a bone than it is to compress it. It's 1.5 times 10 to the 10th newtons per meter squared. Or is it meters squared per newtons? I always get, no, it's newtons per meter squared. Yeah, that makes sense. Because look, when I multiply newtons per meter squared times meters squared, the meters squared cancel, so I get newtons. It's good. Good, good, good. Whoa. All right. So then this comes out to be about 1.9 times 10 to the third newtons. All right, good. Well, let's look at, now, you also have shearing, all right? And the only thing I'm going to talk about shearing here real quick, don't want to lose my place in my book, but here's an example of shearing, okay? Shearing, as in sheep shearing, but it's a different kind of shearing. Let's erase this. Things that don't shear at all, or don't shear very well, are brittle, okay? But this thing shears pretty nicely. And what I mean is when I apply this force, it's uniform force, see how it kind of has an angle to it? If I hold this steady, you can really see it with a big stack of paper, a ream of paper. You can kind of push on it, right? And it'll fold out. In other words, the original stack will look like this. And then you push on it, and you get something that looks like this. Right? Looks like that. That's shearing. Okay? And if this angle is small enough, so something that shears really well, Jell-O. Jell-O shears really well. You can go oink, and it bounces back too. It goes doing, comes back. All right? So that's and the shearing of something, the shearing of something is equal to F over A divided by this little angle of theta, or phi. And because that angle phi, you got the height of the thing times x here, okay? Got the height of the thing times x. You could say really that the tangent of phi is equal to x over h. But as long as phi is small, is less than 9 degrees, then phi is really close to x over h anyway. And so shearing actually just equals F over A divided by x over h. Okay? All right, so let's take a look. Because I have started building your assignment, and I think, like, let's just get used to looking at what one of the problems might say. It says a 4 kilogram object is supported by an aluminum wire of 2 meters, so that's LO, and a diameter of 2 millimeters. How much will the wire stretch if you hang that thing on there? Okay? So let's take a look at this. You guys are going, wait a minute, I thought we were talking about shearing. We're done talking about shearing. Oh, except for one other thing. I just need to show you some things. This is really these things with stretching of materials, Young's modulus, those kinds of things. This is really the crux of a lot of the work that the guys downstairs guys and gals work on, and upstairs too in the engineering department. This is a big area of material science, and solid state is what they call it. In other words, working with different solids, because different solids, different materials can do different things, you know, much better than some, and you have to test them and do all that kind of stuff. And this shearing thing actually ended a heated debate in the physics department. How many of you have toured old Europe? Or nobody has toured around? Oh, what's that? Oh, just anywhere like Germany or, okay. All right, did you go to any old castles? All right, now, those glasses, those windows that have been there a long time, did you notice at the bottom that they're fatter? And so this was the discussion. Is glass a liquid or a solid? Because those things got fatter at the bottom because the glass oozed very slowly over 1,500 years. Some of those castles were built like 600 AD, 500 AD during the Dark Ages, okay? And the glass that they put in there when they first were learning how to make glass, they put it in there and it just kind of oozed. So, is glass a fluid? Because it sure does seem to flow, all right? But it also shears. Think about it. Water cannot shear. You can't smush on water and have it come back, right? It just...
Can a spring shear?
Yeah. If I had a slinky, I could definitely do it sideways like that, yeah. The spring can get off kilter. Yep. And it's a nice solid thing, okay? So that's what ended the argument. Our chair finally said, well, look, glass has a shearing number, okay? And it's really... this angle is really, really small before it shatters, before it hits its breaking point. And so since it does shear, it's a solid. Because the flow rate of glass, I mean, you can't do something can't flow 1 centimeter per 100 years. I mean, come on, that's crazy. All right, anyway, all right, even though it does, but the Earth's slowing down in its rotation too, but we don't talk about that either, all right, because it's so slow. All right, so anyway, so let's take a look. Let's say you've got a 4-kilogram object supported by an aluminum wire. So here you go. Got a 4-kilogram object. He's 4 kilograms. Supported by an aluminum wire that's 2 meters long. And it's got a cross-sectional area of 2 millimeters, which equals 0.002 meters. Okay? They want to know how far it's going to stretch. What are we looking for here? Let's see. We know L is 2.0 meters. We know A is going to be pi times 0.002 meters, or squared, meters squared. What's the force? This is 4 kilograms hanging there. What's the force? Four meters times gravity. Yeah, we're on it. There you go. It'd be mg. 36 plus 3.2, 39.2 newtons. That's the force. And then what do I need? I'm after delta 0. Oh, I'm after for delta. Sorry, that made no sense. I was thinking, oh, I need to put the not in there. Oh, this is all I need. The little sneaky part to that was you got a 4 kilogram thing. Now it's stretching it. Oh, you also need Young's modulus for aluminum, which is in the book. The Young's modulus for aluminum is sorry, 7.0 times 10 to the 10th. Newtons per meter squared. So all I need is that delta O. So that's not too bad. We just go F over A equals Y times delta L over LO. So we get FLO over YA equals delta L. Flow-ya. All right. Yes?
So the 2 meters is aluminum, and then it has a weight at the bottom?
And then we're just trying to see how much it would stretch if it's hanging from something.
If this weight was attached to it and is hanging.
And so we're just trying to see how much it would stretch.
Exactly. Right. That's all we're after. This is your problem number 6, your new homework problem, by the way. So it's this little FLOIA. And you'll probably get a FLOIA on your test. Okay? Type thing. All right? And then I ask a femur question because we got a bunch of pre-health or health sciences people in here. So you got an 85 kilogram person stands on one leg. 90% of the weight is supported by the upper leg. Connecting. So this is a compress. So remember, this one's you're compressing, right? Because the floor is pushing up, you're pushing down, so you're compressing the weight there. And the compression thing on a bone is different. It's like 9.5 times 9.3 times 10 to the 9th is the Young's modulus. It's because it's easier to smush the bone than it is to stretch it. Okay. So that's all. That's all that one is. And you want to do 90% of the weight is supported by the femur. So how much is the bone compressed? So you're looking for delta L here, but you're just taking 90% of the guy's weight on it. Okay, now let's talk about fluids and pressure. Okay, because you're starting to feel that too. Stress equals F over A. This also equals pressure. Okay? This also equals pressure. F over A is equal to pressure. But all right? Now, let's talk about pressure for a second. Well, let's actually talk about him for quite a while. Because we're almost done. We'll be done with this. This is going too quick, but that's all right. Okay. I just want to make sure we get it. Yeah, we might try problem 32, even though I'll be doing physics on the fly again, which is dangerous. But we'll see. We'll see how this discussion goes, because there's a lot to pressure and Pascal's principle. So here we go. All right. Let's get the units straight first. All right, before we start anything, let's get what's going on in the room right now. All right? Let's get what's going on in the room right now. What we've got is, I want everyone to look at your thumbnail. Okay? Look at your thumbnail. All right, that's about 1 square inch, roughly. Okay? How many pounds of pressure are smashing on your thumbnail right now? How much pressure is on your thumbnail right now? Anybody know? Feels like 0 because we don't feel it, but it's actually almost 15 pounds. 15 pounds of pressure is on your thumbnail right now. So you feel all over, right? So if you take your thumbnail and put, in other words, how many square inches your body makes, your surface area of your body is, times 15, because it's actually 14.7 pounds per square inch. So it's like a bowling ball. It's like a big bowling ball. Per every square inch of your body is what is smashing down on you right now, okay, from the air pressure. And that air pressure comes from, right, you go, well, where's all that pressure comes from? Well, if you look real hard, you can see these little air molecules flying around. Well, you can't see them, but anyway. All right, there's these little air molecules flying around at the speed of sound. Okay? That's why sound travels at the speed of sound, because it compresses the air, expands the air, compresses, expands. Okay? And since those air molecules are moving at the speed of sound, that's how fast the speed of sound goes. All right? And what's going on is they're banging off the sides of these walls, they're banging off you at the speed of sound, and a bunch of them. Moles and moles of them. Okay? Moles and moles. And that causes a lot of pressure. That's a lot of force. Per area, those little banging into you, that force per area is a lot of pressure. That's 15 pounds per square inch. And you don't feel it because you're so used to it. Okay? That's why, how many of you have seen the movie 2001: A Space Odyssey? How many of you have even heard of it? Okay, a handful of you have heard of it. All right. Anyway, well, there's a big scene in there. Your parents were probably 3 when the movie came out. But anyway, because it came out in 1969. Okay, so it's old. Yeah. But it was way ahead of its time with all the things it showed. And most of the stuff was pretty scientifically close. It was pretty good. Except for there's one scene where the guy runs through a vapor lock. The evil computer Hal tries to lock him out of the spaceship. Okay, so he's in this like zero pressure chamber. For a split, he's got to run through the zero pressure chamber. Well, what would happen as soon as he hit zero pressure? If your body is used to getting smushed by 1,000 bowling balls at one time, then all of a sudden you take those bowling balls away, yeah, he'd explode. Exactly. He'd expand and his skin would stretch and he'd get all bloated and his eyeballs would bug out and boom, until he reached the shearing pressure of his skin and it ripped apart and sorry. Well, anyway. Yeah, so Stanley Kubrick didn't go that far. Have any of you ever seen? I wish I had called it up, but there's like a. Have any of you ever seen marshmallows put inside a vacuum under a bell jar, and then they suck all the air out of the belt from that thing? The marshmallows just get huge. They expand real big. Okay, and so we feel a lot of pressure on us at all times. All right, and where it comes from is all these air molecules banging around the room, okay, and smashing in over that area. And that's a whole area of physics where they study the movement of fluids and things like that. It's called statistical mechanics, stat mech. It's every grad student in physics' favorite course. Not really, but anyway, where they look at all that kind of stuff. And it's a killer course, but it's where all this came from that we're going to look at right now. Now then, so now that you understand that, the other thing that we need to know, that we need to go into, is this guy, rho, before we get started. Rho is known as density. All right, chemistry people, what is density? Mass over volume. Mass over volume. Now, chemistry people, we're not going to be using CGS, which is what you guys use, which is usually you use grams per centimeters, right? We're not going to cubed. We're going to be using kilograms per meters cubed. Okay? Now, one of my favorite, now this is a test question I guarantee you'll get. You'll get a stretchy problem, and you'll get a FLOIA, and you'll get one of these too. Let's say we've got a gold ball. It's weird. It's a kind of a weird thing. Or I might give you a cylinder, but I'll give you what the equation is to find the volume of a cylinder or of a gold ball. All right, let's say we've got a gold ball. Gold has a density of 19.3 times 10 to the third. The density of gold is equal to 19,300 kilograms per meters cubed. Woo! So, this table right here is about, this guy right here, oh, that's going to slam. That's all right. Oh, no, it's not. Something retarded the torque there. All right, anyway, this is about 1 cubic meter. So if I had a thing of gold this big, I don't think I'd have been dragging it across the floor. Because it multiply this guy by 2.2, and that's about 45,000 or so, 46,000. So gold would be about 46,000 pounds, that size. All right? So we're not going to be dealing with a gold thing very big here, but let's say I got a gold ball hanging from a massless rope. Ooh! No! It's hanging from an aluminum rod. Oh, this is even better. Let's say I gave you a gold ball. Here's the test question. R equals, and the radius of this gold ball is 0.3. It's a big gold ball. Yeah. The radius of it is 0.15 centimeters, or 0.15 meters. How far is it going to stretch that? We've got a 1.5 meter aluminum rod it's attached to. aluminum rod. What's delta L? How in the heck would you find that? Yeah, let's do that problem. That'd be good. So think about it. How would you do that? First thing you got to do is go, oh, I needed mg over here. How do I get mg? Mass times gravity, but how do I get mg over here? What? All right. Bradley's back with us. And it's m equals rho v. There we go. Aha! Now all you need, what's the volume of a sphere? Or I might change it. I might put a cylinder on there. What's the volume of a sphere? Think. 4/3 pi r cubed, right? 4/3 pi r cubed. I should make you derive that using triple integrals and polar coordinates. What? Yeah. Okay. All right. So that would be a fun test question because that would combine a little bit of everything. Now, since we've done this, but one of my favorite questions though with this is, what if the tension in this rope, let's say we've got a massless rope that we don't want to stretch now. Let's say the tension in the rope is 300 newtons. What's the radius of the ball? Well, you do rho v again times g equals 300. And then you got to, so you'd have, rho v times g equals 300. And so you get v equals 300. This is what I used to give, but now I've got another reason to live. This is cool. 4/3 pi r cubed equals all this. Then you got to tease your r cubed out of there. And then the hardest part is figuring out how your particular calculator finds a cubed root. One way to do it is you take the number, whatever number you get, I don't know what it would be, to the 1/3 power. That's one way to find the cubed root. Take something to the 1/3 power. But anyway, I'm not going to do that to you. We're going to combine it all together. Okay. Or I might give you, that's what we'll do. You'll have to do that, and then we'll stretch it. That'll be good. All right, now, but we'll also talk a little, we'll have, I know I'll have an Archimedes problem on there, okay, which we'll talk about on Thursday. But right now, let's find out a little bit more about pressure in still water. Pressure and depth, okay? All right, so we got one of the big test questions done, the other big test question, so you don't forget, remember what we're going to do. Again, it's going to be a rolling sphere. It's going to be a sphere coming down a ramp. He's going to smash into a spring. All right? It's just one of those energy transfer problems, just like on the last test. Everyone kind of screwed that up. So I'm going to give you a chance to redeem yourselves and everything. So it'll be good. So you're going to have this big rolling sphere. It's going to roll down a ramp, smash into a spring. Then you're going to find the radius of this ball, and then we're going to see how far it would stretch an aluminum or whatever string. Now, or rod, or maybe copper. But I will give you the Young's modulus. I will give you that. Okay? So that won't be bad. So there's two of the questions out of the way. Probably only have 4 or 5 questions, so there we go. All right, now. Oh, and we'll definitely have a GM, F equals GM M over R squared thing. Okay? Definitely something like that. How high you have to be up if you want your weight to be 50%, or how high do you have to go to be weightless from the earth? That kind of thing. All right, now, so here we go. Let's take a look at pressure and depth. That's right, still water. Okay, basically I've got a beaker of water. Okay, got a beaker of water here. All right, and I'm going to take aluminum, a piece of it right here. All right, going to take a piece of that thing. Front view of this column of water that I've just taken out, mg. I want to find out what the pressure is going to be right there. I want to find out what the pressure is going to be right there. Then we'll talk about hydraulics and all that stuff here in a minute. All right. Now, here's the deal. There's two. The pressure right here, there's a total pressure. Now, there's a pressure that it feels because of the weight of the thing, okay, pushing down on it. All right. And it's also got a pressure up here, P naught, which is our 1 atmosphere thing, which is our 1.01 times 10 to the 5th pascals. Always. Because we're going to do all these problems since we've got to go through this material so fast. 1.01 times 10 to the 5th, just to give you let you know what that means. It's about 1 atmosphere, which does equal 14.7 pounds per inch squared. Okay? All right, so it's got some pressure there. Plus it's got the mg, the pressure caused by the mg. Now, so the actual weight that it feels down here, the force that it feels down there is rho times v, right? Which is what we got from over here. Because we know that mass is equal to rho v. And so the mg of this thing, so mg equals rho v times g. Right down here. And this is water, so the rho is 1,000 kilograms per meters cubed. Okay? So, the actual pressure then is equal to the pressure at the top plus rho times g times h. How did I get that? How in the heck did I get that? Well, the book doesn't, your book just kind of jumps right into it, which I thought was fine with me. That worked. But in semesters before, I've done it by using the free body diagram. You've got two forces here. PO is equal to the forces over A. So you got PO times A. Okay? That's the force at the top. The force caused by the mg would be rho v times g times g. Okay, so those two are added together equals the final force times the area. Okay, now what we do is we divide out all the areas, which is the same. Okay, and when you divide out all the area, you wind up with this was just, there we go. That equals that total force, and you divide out the area to get the final pressure. Now, volume divided by area gives you the height. Okay, because volume is the cross-sectional area times the height, and so when you divide that out, that's how you get this rho gh. There's your pressure formula in still water. Because when something's moving, it's got less pressure. The faster something flows, the less pressure it has. Okay? Mother Nature doesn't like that. And so when there's less pressure, she's always trying to fill that void. So she's trying to send energy in there. And that's what causes those Bernoulli effects that we will look at on Thursday. I'll bring in some kind of cool demos that are kind of fun. All right, so P equals PO plus rho GH. All right, now let's look at the first example of this. It says, what's the total pressure on the back of a scuba diver in a lake at a depth of 8 meters? Okay, so you got the scuba diver, and he's down below the water at 8 meters. First of all, he feels the mg of that water on his back. Okay, and the pressure is that force, that mg, divided by the A. Okay, and so he's down at 8 meters, and here's what he feels. The pressure he would feel would be the initial pressure at the top of the water, okay, which is the good old air pressure on top of the water, plus the rho of H2O, the rho of the water, times the G times the 8 meters. Well, that's not very bad. This is equal 1.01 times 10 to the 5th pascals, plus this would be 1,000 times 9.8 times 8. That comes out to be 0.754 times 10 to the 5th pascals. And so this all comes out to be about roughly 1.8 times 10 to the 5th pascals. Okay, that's the pressure he feels down there. Which, this is real close to about 1.8 atmospheres. So it's about, he feels what you feel right now plus double it, almost double it. Okay. All right, so that's not too bad. But what's the actual force? The next question is, what's the actual force caused by this? What forces does the water cause on him? And that's huge. Well, we found out that the F over A is equal to rho H2O times G times 8.00. Okay? So we've got F equals rho times H2O times G times 8.00 times, they said that the area on his back, just the specific area on his back that we're looking at is 0.6 times 0.5. They gave us a 60 centimeters by 50 centimeter area. So it's 0.6 times 0.5, so you multiply all that out, and the force comes out to be huge. It actually turns out to be like 2.35 times 10 to the 4th newtons when you multiply all this out. Which is actually about 2.6 tons. All right? The book put an exclamation point. So that's not, for those of you that are mathematical purists, that's not 2.6 tons factorial. Kidding. It's a little math joke. All right. Okay. That's a lot. How many of you have gone down and jumped off the diving board, gone down and touched the drain? Okay. Well, that's only 10 feet, so that's about 3 meters down. But this is, and you're feeling quite a bit of weight down there. You feel all that pressure. That's that pressure on the ears that you're feeling. Okay? And I hate that feeling. That's why I never got into scuba diving. You know, I lived on Okinawa for 6 years where the scuba diving is great. But I was like, I'll snorkel. I'll just paddle around, snorkel all day long until you start seeing sea snakes. And then you're like, whoops. I'm out of here. None of that. All right, now, this is a great place to look at Pascal's principle. All right? This is Pascal's principle. Basically, boy, I wish I had brought in my demo bag, but I forgot it. Okay, so let's do a thought puzzle. You blow up a balloon, okay, and you tie it off. Got a nice little balloon, all right? Now what happens when you squeeze it in the middle? It kind of bulges out on one side, bulges out on the other side, right? So it felt a change in pressure on the inside there. And whenever you change the pressure, it's the same throughout the entire system, okay? So one pressure change in one place equals the same pressure change in another place, all right? That's the big idea. Now, but before I go on, oh, and we got one quiz question too when we're done. Don't forget, don't let me forget the one quiz question that we're going to have when we're done. But anyway, now, the big idea is that this equation depends solely on the pressure that you feel, depends solely on the height of something, okay? On the height of the water. Has nothing to do with how far back it goes. So a strange thing to get used to is that Hoover Dam, which is huge, and it's really thick at the bottom, and Lake Mead, which goes on for like 27 miles from Hoover Dam back behind it, you'd still need that big, thick bottom, even if Lake Mead was only this wide. But it was still as tall as it is, as deep as it is there at Hoover Dam, okay? Because the pressure would be the same. The lateral stuff doesn't do anything to the pressure. It's only the depth. However, imagine you're in an aquarium, okay? Imagine you're in an aquarium. All right, oh, let's say this room's an aquarium. Glub, 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 glub. Well, actually, we are in an aquarium because a lot of people treat air just like a fluid, okay? So we are in an aquarium. But if it was filled with water, it'd be a lot heavier. So we're all in our little scuba tanks and everything, okay, and we're in an aquarium. The pressure right here is the same as the pressure here, is the same, as long as I'm staying at the same height, the pressure is the same, okay, that it feels. Okay, pressure is a scalar too. So the pressure here is the same as the pressure coming up right here, the pressure pushing down right there. They're all this, it's all the same number, okay? It's all the same. It doesn't matter, okay? So it only depends upon the height. So now, let's talk about hydraulics, okay? Let's talk about hydraulics and the hydraulic force multiplication. And basically, due to Pascal's principle, here's what, I like the way this book writes out the laws. They actually make sense. It says that pressure applied to an enclosed fluid is transmitted undiminished to every point in the fluid and to the walls of the container. That's what we're talking about when you squeeze the balloon, okay? The pressure applied to an enclosed fluid is equal to the pressure yada, yada, yada. All right, so let's look at this first problem of hydraulics, and then we'll do the quiz, and we'll be done. All right. Well, shoot. You need the equation for what Pascal's principle means. That means the force coming out divided by the area of output is equal to the force going in divided by the area of the force going in. Okay? What happened to my good marker? I guess that one was it. Now, so what does that mean? Let's just read the problem then. So we can also get the output force, there we go, is equal to A naught over AI times Fi. All right. So let's say I've got this. I've got a garage lift. Has input and lift output pistons with diameters of 10 centimeters and 3 centimeters. Okay? So the output area is equal to pi times 0.3 meters squared, and the input area is equal to pi times 0.1 squared. Okay? Now, I want to lift, I think it says, all right, the lift is used to hold up a car with a weight of 1.4 times 10 to the fourth newtons. Wait a minute. It's 1.4 times 10 to the fourth newtons? Remember the scuba diver 8 feet under? He's got more than a Honda on his back down there. All right. Anyway, so, all right, so you got, that's the output force then is equal to 1.4 times 10 to the fourth newtons. How much little force do I need to apply? Oh, this is too, you're probably going, well, this seems too easy. Wait a minute, did I not do this right? Oh, I need, okay. I need this guy. Okay, first of all, let's think about this. Let's think about this. What's the ratio of the radius of the output to the input? 3 times. And we're squaring them. So how much times greater is this force than the input force? 9 times. Okay? So in other words, I only need to put in 1/9 of the force. Okay? 1/9 of the force will give me this much output force. Okay? But let's go ahead and do it anyway. So we're after Fi. So I got to rearrange this a little bit, and I'll go FO times AI over AO equals DO, no, equals Fi. So my pi's cancel, and I wind up with 1.4 times 10 to the fourth newtons over 0.1 squared over 0.3 squared, and that's going to come out to be basically 1 over 9. Okay, so it's just 1.4 divided by 9. Now, you might be like, oh, so if I get my area big enough, I can really lift a lot. Yes, you can. But the problem is, if you think about it, which I didn't, I read the book and they told me, hey, now think about this. It means, it says here, I'll just read the way they say it. However, don't think that you getting something for nothing with a large force multiplications. Energy is still a factor, and it can never be multiplied by a machine. Okay? Why can't energy ever be multiplied by a machine? Yeah, because it's constant. Energy in the universe is constant. I can't create, if I come up with a machine that can create energy, whoo, I'll make a lot of money. All right? But I can't. All right, maybe I can get an antimatter machine or something like that. All right, but anyway, and it says, looking at the work involved and assuming that the work output is equal to the work input, an ideal condition. Why? Because there's no energy lost to friction or heat or sound or chatter, any of that kind of stuff. Then with W equals Fx, in other words, force input equals force output, and you've got X naught equals X, Fxo equals Fi x1. In other words, what happens is where XO and X, so this is what they're saying. For the energy, for work, force times distance, this will be the last thought I leave you with. And it's not testable, so you can just kind of sit there and relax for a second. In other words, plop, snore, okay. All right, this is what they're saying. Okay, and if this guy's really big and this guy's a lot smaller, then this guy's got to be really big. In other words, I'm going to have to move him. In other words, if I want to lift a car with very small force, I'm going to have my plunger like 100 meters high. Okay, so I can push it that far to get it to rise just a little bit. See what I'm saying? You see that? Okay. All right. Okay, now here's your one quiz question. Mr. Waters might get this one right off the bat. He's the only one I'm expecting to get it right away. Besides Ting Yi. Oh, Ting Yi, since you're late 8 minutes, you're going to teach class for 8 minutes on Thursday. Kidding. Relax. It's fine. You just had Hal all upset. He pulled his hair out. Okay, here's the one and only question. What happened in Tun Tavern, Philadelphia, in Philly, Philadelphia, boy, if I could spell, PA, on November 10th, 1775, which is 200 and some odd years ago today. 225, what's 25 plus 19? 44, 244 years ago today. Anybody have any ideas? Nope. Mr. Waters knows.
Just give us a couple seconds to Google it.
Oh, okay. All right, you got to Google it on the iPhone. Nobody knows? Except for Kevin? No, not a thing to do with physics. But it's the thing to do with the history today. All right. First hint. Hey, here's your first hint. Simplify. Okay, that should be the second question. What does that mean? All right. Exactly. There we go. So that's what happened November 10th, 1775. My Marine Corps came alive, as they used to say in their little jokes. What? The Marine Corps was born November 10th, 1775. In Tun Tavern, basically what they did was they got a bunch of guys drunk, and then they woke up, they were on board ship, and they were told, hey, you're pirates now for the Continental Congress, okay, for the Continental Army. Okay, they impressed them into service, said, we'll give you $3 a month or whatever it was, and a mule.
So what is Semper Fi?
What? Semper Fi means, oh, okay, how many of you have sang this at Christmas time? What song is that? You've heard it this way.
Oh, come on, you faithful.
Right. This means it's Semper Fidelis. It means always faithful. You knew that much? You knew that much? Okay. Well, anyway, yeah, that's what they did. And basically, the first Marines were pirates for the revolutionaries. They would board the ships. That's how they got the name leathernecks, because they wore these thick leather saddle type things around their neck to keep swords from cutting their jugular and stuff like that when they were boarding parties. So anyway, all right, there's your quiz.